All right, let's jump right into this. Welcome to the Explainer. Today, we're taking a deep dive to demystify a massive and quite literally groundbreaking shift happening right now in advanced semiconductor manufacturing. Look, if you track this industry, you know we're hitting a physical wall. So today, we're going to break down the exact technologies letting us climb right over that wall, comparing the reliable traditional methods with the absolute cutting edge. We've got a lot of ground to cover, so let's get to it. Here's a quick roadmap of where we're headed today. First, the 3D packaging shift. Second, traditional back-end wire bond. Third, advanced front-end CoWoS. Fourth, a direct wire bond versus CoWoS showdown. And finally, Section 5, die-level tracking. Starting us off with Section 1, the 3D packaging shift. Okay, so here is the multi-billion-dollar question the whole industry is asking. How do we actually beat the limits of Moore's law? We all know advanced mass production has successfully pushed nodes down to 5, 3, and even 2 nanometers. But to really put that into perspective for a second, a single strand of human DNA is about 2.5 nanometers wide. Going smaller than that is an almost unimaginable engineering headache. So if we can't easily shrink the transistors horizontally anymore, how on earth do we keep boosting performance while saving power? Well, the answer is 3D packaging. Instead of laying individual chips flat next to each other on a wide printed circuit board, the industry is building skyscrapers. By stacking integrated circuits, or ICs, vertically on top of each other, we can massively increase integration, supercharge computing performance, and drastically cut down power consumption. It's a total game changer. But it begs the question, how exactly do we stack them? That brings us to Section 2, traditional back-end wire bond. What's really fascinating here is just how physical this traditional method actually is. In traditional back-end packaging, facilities use wire bond and die bond tech. Basically, you take the die, secure it onto a substrate or lead frame, and physically stretch out microscopic wires, usually made of gold or copper, to connect the pins of the different ICs. By stacking package onto package like this, you get that multi-layer 3D effect. It's mature, it's reliable, and the industry understands it inside and out. But here's the catch. This traditional method has some pretty severe limitations the minute we push for ultra-high performance. Because you're physically pulling these tiny wires, your connection density is naturally capped. We're talking distances between connections of roughly 15 to 20 microns. Now remember, those front-end processes working at 3 to 5 nanometers? That precision gap is astronomical, literally thousands of times apart. Plus, pulling physical wires means your signal has to travel a longer distance. And in electronics, a longer signal line has to be a thicker line, which directly translates to higher power consumption and a lot of unwanted heat. But hey, don't write off wire bond just yet. It is incredibly cost-effective and still miles ahead of wiring separate individual chips across a standard circuit board. Because it's mature and cheap to mass produce, this kind of back-end 3D packaging is absolutely perfect for low to mid-speed applications. Think of things like automotive processors, microcontrollers, and CMOS image sensors. It absolutely gets the job done there. Moving on to Section 3, Advanced Front-End CoWoS. Enter the heavy hitter, CoWoS. This is TSMC's ultra-advanced 2.5D and 3D packaging tech. The acronym itself stands for Chip on Wafer on Substrate. Now, the revolutionary shift here is mind-blowing. Instead of a back-end plant using physical wires, a front-end semiconductor plant uses a silicon interposer. They literally use front-end yellow light photolithography, the exact same high-tech methods used to manufacture the chips themselves to create the connections between the chips. Let's break down how they actually pull this off. First, they grow what are called microbumps directly onto the CPU or GPU die. Then, those bumps are connected straight to the silicon interposer. Picture this interposer as a microscopic, flawlessly precise printed circuit board. But rather than screen printing standard lines, they use semiconductor-grade manufacturing to etch the connection routes. This lets them seamlessly route thousands of I/O signals between the processor and memory with absolute pinpoint precision. And that leads us to the next massive leap, TSV, or through silicon via. Say you're stacking identical chips, right? Like layers of high-bandwidth DRAM. Their data buses and addresses line up perfectly. So instead of wiring clumsily around the outside of them, TSV literally punches a vertical connection straight through the silicon itself. It's exactly like an elevator shaft in a tall building, perfectly connecting the upstairs floor directly to the downstairs floor. The signal just shoots straight up and down. Because of that silicon interposer and the TSV elevator shafts, transmission distances become ridiculously short. And what did we say earlier?
Short distances mean lower power consumption and significantly less heat. On top of that, CoWoS totally eliminates the signal interference you normally get with traditional wires at super high frequencies. This is exactly why this highly integrated tech is the absolute gold standard for the AI revolution. We're talking AI accelerators, high-performance GPUs, 5G, and high-bandwidth memory.
Let's pull it all together in Section 4, Wire Bond versus CoWoS. So putting them head-to-head really crystallizes things. Back-end wire bond uses gold and copper wires, while front-end CoWoS relies on that silicon interposer and TSVs. Wire bond deals with long signal paths and a lower I/O density of around 15 to 20 microns. CoWoS, extremely short paths and massive off-the-charts density. But of course, that kind of hyper-performance comes at a premium. Wire bond is your low-cost, mature, high-yield workhorse. CoWoS is your highly advanced, premium-priced powerhouse. At the end of the day, you choose your packaging based entirely on what your final product demands. Finally, Section 5. Die-level tracking. Now, no matter which method you use, there is one absolute necessity tying the modern smart factory together: die-level tracking. Whether you're running back-end wire bond or advanced front-end CoWoS, your manufacturing system has to maintain total, uncompromising traceability. You need to know the exact X and Y coordinates of every single die from the original lot wafer and precisely which interposer or substrate it ended up on. Think about it. If a high-end AI chip fails, engineers have to trace back exactly which die from which specific wafer caused the hiccup. Full process traceability isn't just a nice-to-have anymore, it is strictly mandatory. Which leaves us with something pretty critical to chew on. The hard physical limits of shrinking chips are forcing this entire industry to build upwards, adopting intensely complex, microscopic 3D routing technologies to survive. So, as semiconductor packaging aggressively moves into the 3D space, is your manufacturing traceability truly ready to follow?